Okay. First of all, I want to say thank you to the organizers for the opportunity of presenting this work. This is something. Okay. Bend it. Okay. Well, this is something I have been working in a paper I published last year and some work in preparation that I'm doing right now. As the title say, I would like to make some connection between a lambda model, which is an integrable deformation of a Green-Schwarz superstring. It is a field theory in 1+1 dimensions. It is a constraint field theory. And the idea is to connect it somehow, rewrite it in terms of a gauge theory in 2+1 dimensions, which is of Chern-Simons type. To do so, I will need to make a very careful introduction of the spectral parameter on the 2+1 dimensions. The basic idea is to show you how the boundary, the theory that lives on the boundary of a solid cylinder is precisely the lambda model. This is the main goal is to avoid the problem of the non-ultralocality of the lax spatial lax component, the Poisson bracket of the spatial component of the lax connection. So let me see if this is working. So this is the content of the talk. I would like to. How do I come back? Okay. So first of all, I would like to make some comments about the Green-Schwarz sigma model on FDS phi cross phi, just to set the notation and the algebraic structure behind. Then I move to the introduction of the lambda model itself, and show you how we can connect both theories. Then I would like to present some key relations that suggest the connection with the higher dimensional theory. Then I will comment on some properties of lambda model that has been published in the few years. Then I move to work on the classical integrability through Hamiltonian analysis. I need to run the Dirac algorithm. This is a tedious but necessary part of the construction, the connection of both theories. This allows me to construct and extend the lax pair in a unique way. And then it is in this point that the Chern-Simons theory starts appearing. Then I move to introduction. This is the spectral parameter dependent with some loops on the disk. This is a part that is in progress. And then I'm coming, make some final comments and perspectives. So, well, this is well known. Let us consider the Green-Schwarz action of on the hollow sphere, which is a closed string. R is time. S1 is the coordinate along the closed string. This is the notation I will use. The brackets are super trace in some faithful representation of PSU 2,2/4. The J's are flat currents written in terms of this group element F that belongs to the Lie supergroup, and theta denotes a combination of projectors along the Z4, the composition of the Lie superalgebra PSU 2,2/4. So all this is well known. The Euler-Lagrange equation of motion of the Bena-Polchinski-Roybal-Lax connection is this one. It is flat on shell, so we can reproduce the equations, the Euler-Lagrange equations of motion of the action. There is a convenient way to start the Hamiltonian analysis in order to avoid some non-local integrations in the definition of conjugate momentum. Is to write the action in first order form. So I trade the currents for some gauge connections, A plus and A minus, and enforce the flatness condition through a Lagrange multiplier, which is called nu. So when I do so, when I use the equation of motion for the Lagrange multiplier and enforce the flatness condition, I recover the action, the original action. This can be also interpreted as an abelian version of the Bush approach to T-duality. So the lambda model, which was introduced in this paper in collaboration with Tim Hollowwood and Luis Miramontes, is this one. So this is our final product. It is written in terms of a f mod f with a model plus a term that mimics the Green-Schwarz action I brought before. So K is the level. Sigma is the same worksheet. A plus and A minus are the same gauge connection introduced in the first order formalism. F is again an element of the PSU 2, 2/4 supergroup. A plus minus is the connection, and this omega is a projection. It's a combination of the 4 projection along the Z4 decomposition of the algebra, and lambda is defined in this way. G is the coupling constant of the Green-Schwarz model, and K is the level. So this is where the model picks the name. There are 2 interesting limits. The first one is as lambda goes to 1, big level, G fixed, and expanding the group element around the identity, so the action reduced to the non-abelian Bush's form, or the first order form I wrote before. So then again, using the equation of motion of the Lagrange multiplier, we can come back to the Green-Schwarz action. The other limit is as lambda goes to 0, so I need to pick big G and K fixed, and in this way I can construct a current perturbation of a gauge Besson with a model, and that is very close and intimately related to the Polymerase reduction, just in the same Polymerase reduction performed by Grigoriev and Sailin. So the integrable structure is exactly the same on both theories. The lax connection takes exactly the same form. The analytic dependence of the spectral parameter is just the same, but it's written in terms of some dual currents. These currents are expressed in this way. So F is actually group Lagrange multiplier, which we end up with a kinetic term, so we give some dynamics through the gauge Besson with a model. So the equations of motion for the gauge field are written take this way in terms of 2 Kac-Moody currents that are just standard currents on Besson with the models. They mutually both commute. There is a consequence of this connection, of writing things in terms of Kac-Moody currents. And if I call these 2 powers, square root and inverse square root of lambda, Z plus minus, which I will call poles, the spatial component of the lax connection, when it hits these 2 specific points, becomes the 2 Kac-Moody currents. So this means that the monodromy matrix, when it in the complex plane it hits these 2 poles, it becomes the monodromy of 2 Kac-Moody currents. And it's shown by FADF. This leads, after quantization, this leads to the existence of finite dimensional quantum groups, at least for compact groups and when things are well behaved. Now, on-shell, by on-shell I mean using the equation of motion for the gauge field and the F, calligraphic F, we can write it as a compatibility condition involved with this wave function. So this allows to write all the Lagrangian fields in terms of this psi. This is important. The first relation here, the F, it mimics exactly the same form as a chiral Besson-Witten solution when we solve the version of the non-abelian wave equation where the two chiral sectors instead of the Lycon coordinates splits, it happens something similar, but the decomposition is not chiral. So I need, in order to construct the Lagrangian field, the solution to the equation of motion, I have to consider the wave function evaluated at these two poles. So the other expressions take that form, and I can evaluate the action on shell, and I see something, some sort of a splitting on the complex plane. So the phase space information is completely contained of these 2 points. This is the key relation. The F is a key relation that allows me to ask if there is a possibility to relate this theory with a Chern-Simons theory, just in the same way if a chiral ordinary Witten model can be written, can be related in terms of, can be related with a Chern-Simons theory. This was done by Witten in the 80s. So the idea now is to exploit, if, to study if this situation also holds in this setting. So before I continue, I would like to make some comments of the general property for lambda models. They were introduced by Svetsos for the principal chiral model, and later on, 1 year later, by us in that work I referenced before. This is a theory that preserves the integrability. The integral structures are just the same, but breaks the global left action of the netter symmetry of the sigma model, and this re-emerges as a Poissonly groups on the lambda model deformations. We brought this in that paper. It also works as a regularization of the sigma model spectrum, which is truncated by the level, just in similar as representation of the Cox-Moody algebra are limited by the level. So when we allow the level go to infinity, we go to sigma model, and the spectrum become more and more bigger and bigger and bigger, and we recover the giant magnum spectrum. An interesting fact is that it implements the Faddeev-Reshtikin ultralocalization mechanism directly on the action functional. So this was only, it's new that it only worked for the principal chiral model, but now we have a Lagrangian version of it. Well, we also made some relation with the Green-Schwarz case in the parametric reduction for the lambda zero limit. Important is that it doesn't break the local symmetry, so we can still remove all these spurious degrees of freedom and doesn't without affecting the dimensionality of the spectrum. So it is also a symplectic deformation of the sigma model. The dispersion relation breaks the Lorentz symmetry of the dispersion relation of the gauge-fixed theory, breaks the two-dimensional Lorentz symmetry, but in a controlled way in terms of this parameter lambda. So this, the next point was work by Tim Hollywood. He showed that the beta function of this of lambda, but one exact in lambda, but 2 order 1 over k, it vanishes. So this is a marginal deformation to this order. But I did the same for the hybrid formalism. It was just is the same situation. Well, there is another property of the hybrid superstring. There is a sector in phase space where there is a relativistic splitting in the currents along constant direction doesn't mix. Well, and this is the most important part. There was 3 papers written by, well, not by us, where they construct explicitly the background fields of in different cases, and they showed that this theory produces genuine string backgrounds. So the main goal is the following: to explore the lambda model Chern-Simons theory link in order to bypass the old problem of the non-ultralocality, in this case for the deformed superstring. So this L, the special component of the lax connection written before, doesn't obey the Maya algebra. And the reason is that is because we are dealing with a constrained integrable field theory, so we need to use heavily Dirac procedure. I will write it. See ya. Or we can fix this by constructing a lax pair extension outside the constraint surface, such that we make two minimal requirements. The first one is that this lax connection is strongly flat, so it means that it is flat on the whole phase space, not only on the constraint surface. And the extended monodromy matrix, or traces of it, generate first-class functions. So in this way, we can preserve the constraint surface where the lambda model motion takes place. By doing this carefully, we can systematically find the footprints of the Chern-Simons theory. So the Dirac procedure is the following. We have two brackets that are on the phase space, that describe the phase space of the theory. We have two Cox-Moody currents, so we can see in my notation this delta sigma prime is just a one-dimensional Dirac delta function, and the delta prime is a derivative with respect to the first sigma, and the conjugate pair for the gauge fields. The canonical Hamiltonian is this one, so because of the action doesn't involve time derivatives of the gauge field, we have a primary constraint, which is just the conjugate momentum of the gauge field. This leads to two secondary constraints, C plus and C minus, which are just equivalent to the gauge field equations of motion. So with this, I construct the extended Hamiltonian with U and mu are just Lagrange multipliers, and run again the Dirac procedure to check stability of these constraints. So there are no tertiary constraints. We can fix a lot of Lagrange multipliers. In particular, I write this for the kappa symmetry, which then after I have this full set of constraints, I need to split them into first class, second class. The first class primary constraints are those presented there. They only depend on P, obviously, and we can gauge fit them by making these choices. In this way, I can kill the current A plus 3, A minus 1. This is equivalent to the partial gauge fixing done by Grigory van Zyl on the parametric reduction. So we still have kappa symmetry left. The second class pairs, which I can construct between primary and secondary constraints, are those over there. Okay, so these are carefully chosen because I don't want to spoil the Dirac bracket. I don't want to spoil the Cox-Moody algebra structure of the theory, so it is protected. So at the end of the day, we realize that the Cox-Moody algebra is still the same. The fields P are completely eliminated, and all the constraints chosen before can be imposed strongly. So I can write all the dual currents in terms of Cox-Moody currents. Alpha is a combination of these two poles on the level, and the only remaining constraints are these 5, 0, 1, and 3. Grade 0 generates gauge transformation. 1 and 3 are partially first class and second class, which is a characteristic of the Green-Schwarz theory. The first class part is fermionic and generates kappa symmetry. So the phase space is completely parameterized by the Cox-Moody current, and in this partial gauge, the lax pair takes this form, and this is important. It is written as an expansion of around 0 and infinity. This is a fact that I will use later. We are in a conformal gauge, so we need to impose the Virasoro constraints by hand. It is a well-known fact that in order for the Virasoro constraints to be first class, they must be shifted by the fermionic constraints. So I need to put some coefficient that turns out to be the same, Z plus. And T plus plus and T plus minus minus are the components of the usual stress tensor that we find after temporarily introducing the two-dimensional worldsheet metric. In this case, they have some contribution that are quadratic on the constraint. This is not a common feature of the original Green-Schwarz action. So you can see that as k is very big, these terms disappear. So the momentum generator requires a modification in order to satisfy what we expect a momentum generator satisfy, which is translations, rigid translations along the string. So without that phi 0 constraint, the momentum it doesn't work the way it should be. So we need to extend this term. It's unique. So we are safe. We have our P. The P bar means this is the final quantity I will use as an extended quantity outside the constraint surface. So this is the final answer. We need to make some maneuvers here in order to define time flow. So in order not to spoil the first class property and to preserve the motion on the constraint surface, we need to add at least terms that are quadratic on the constraints. So we put some f, 1/2 on the t++ and 1/2 the same amount on the t minus component. This doesn't change the form for the momentum generator, but it changed the form of the Hamiltonian. So we are modifying slightly time evolution on this phase space. I need to, if we choose this f in this particular form, quadratic in the phi 1 and phi 3, something happens. The H becomes the boundary contributions to the canonical Hamiltonian of a Chern-Simons theory on the disk. So once we have the t++ and the t minus, so our strength tensor extended quantities, we can construct a strongly flat extended last connection. So to find the extended or the Hamiltonian Lux pair, we need to compute the action of the momentum, the light cone, translation along x plus and x minus and the light cone components of the worksheet on the Cox-Moody current. So I operate with this. I need to find this Poisson bracket. And it gives this answer. I have to construct, if I need to construct an L plus and L minus depending of this Z in such a way that when this component hits these two poles, it reproduces these extended expressions. So the L plus on the right hand side and the L minus are just the same, the conventional or the Lux pair I wrote before in this particular gauge, partial gauge. So we are not finished. Because the extended P must generate translation, the first conclusion is that that result brought before, in which the on-shell Lux pair becomes the Cox-Moody currents, must be valid on whole phase space, but just for these 2 points. There is a solution to this. There is a proposal to this, a solution that for this L that obeys these 2 conditions. You can see this information comes from the hybrid superstring. I do not have to deal with constraints, just the 0 constraints. I don't have kappa symmetry there, so I can find the answer easily. So it's written in this way. It is a combination of the 2 Cox-Moody currents with 2 operators that depends on the spectral parameter. This omega bar is different from the omega I wrote before. This is the omega operator for the lambda model of the hybrid superstring. So you see the analytic dependence of C is different. Because of the Cox-Moody structure of this theory, I can very carefully compute the bracket of these 2 spatial components of the Lux operator, and it takes the form of the Maillet bracket. So it involves an R and an S matrix, which are not dependent of the field content. They are constant and depend of C and W. You see that the derivative of the delta function that appears in the Cox-Moody algebra propagates again, and it's present in that two term, which is the problematic one in ultralocal theories. It is called non-ultralocal just because both derivatives of the delta function. So the algebra of the monodromy matrix, as Mayet showed in the original paper, is plagued of ambiguities. We cannot compute it. So it escapes the possibility of using the algebraic Betanzat. So this is a very old problem. So the R and S are the symmetric and anti-symmetric parts of this R matrix. C12 is the tensor Casimir, which is decomposed along the Z4 different Z4 subspaces of the Lie superalgebra. Each term is accompanied with a specific power of Z and W. And phi, this 5, is the so-called deformed twisting function. So these two, Z plus and Z minus, turns out to be poles of these twisting functions. That's why I call it poles. So I will make, in the same way in the partial gauge fixing introduced before, the lax pair splits as a expansion around 0 and infinity. I will do the same here. In this way I can recover I can find the final answer. So this is our extended lax pair. It depends obviously of lax pair and combination of constraints. So it satisfies when they hit the poles, they satisfy all conditions that we've found before. So this is the final answer. Using this, I can construct the time component in order to find the equation of motion that outside the constraint surface. So there is something we need to check, and it's the strongly flatness. The F term I introduced in the Hamiltonian is required for this extended lax pair to be strongly flat. Otherwise, we cannot find. Otherwise, it is not strongly flat. So we need to extend the Hamiltonian exactly the same way in order to guarantee that this is a strongly flat lax connection. So we can show also that the action of the T plus plus T minus minus on the lax pair takes this form. And from this, we can prove the conservation of the monodromy matrix. So the extended Hamiltonian at the moment to take the quadratic form. Only after doing all this careful process of adding constraints, sometimes quadratic terms on the constraint, we can write H and P in a quadratic form. I mean, as powers of the lax of the components of the lax pair. You can see the splitting again. There are two special points in complex plane where the phase space information is contained. We can also anticipate that we can construct two Besumino-Witten theories with opposite levels because of the relative minus that appears there. So keep in mind the dependence of H, which is L tau, L sigma. So let's consider the monodromy matrix that is constructed with this extended lax operator and the constraints that we have gathered into this big phi. The 3 phi, a small phi, and the T plus plus, T minus minus. So if I compute the Poisson brackets just for the phi, I found this answer. So the constraint along grade 0, they generate gauge transformations because of the form of the commutator, but the phi 1 and 3 doesn't. They depend of a term that is inverse of the twisting function, but linear on the constraints. So this phi is this. I put some test functions in order to compute the bracket. So this is at we have a twofold interpretation. It means that if I consider these expressions weakly by imposing the constraints, the traces of the monodromy matrix is a first class object, so we can preserve. So all the symmetry flows generated by the conserved charges of this monodromy matrix preserves the evolution, or preserves the constraint surface, which is what we wanted. But at the poles of the twisting function, we can cancel the second terms and reinterpret these three constraints as generating gauge transformation strongly. Notice that are included even the second class parts of the fermionic constraints. So if we want to gauge fix the theory, we need to fix only the conjugacy classes that are related to the kappa symmetry, which are the first class, and to gauge degree 0. So there is an enhancement of gauge symmetry, which is easily seen by considering this generator. So it induces this full action of PSU on the monodromy matrix, but just on the poles. But if I consider these particular forms for the gauge parameters, I recover the result of before. So in this way, I can always keep track of which is gauge symmetry generated associated to the lambda model and which not, which is a result of the extension of the quantities outside the constraint surface. There is something called the dressing gauge, which fixes just the right conjugacy classes and selects the true lambda model physical degrees of freedom, which is the spectrum is Magnon-like. So the summary is the following. I have this Hamiltonian, which depends of only written in terms of the completely written in terms of the lax, extended lax operator at the two special points. There is a gauge generator that comes from some Hamiltonian procedure of extended everything outside the constant surface, and we still have the same Kac-Moody algebra. There is an interesting fact, and it's that the Maillet bracket, when the Maillet bracket is evaluated in these two poles, we reproduce these two Kac-Moody algebras. So the Chern-Simons theory that comes here is the following. I need to consider two copies with opposite levels, but in a Hamiltonian way. So I work on the solid cylinder, and the direction that is perpendicular to the disk is interpreted as time. So we can see there is a boundary contribution. So each copy is associated to a point plus and to a point minus in the complex plane. All these fields are valued on PSU 2,2/4. So the equations of motion are as usual. The first one is that on the bulk or on the disk, the gauge field is flat, and the other condition is written, it's completely flat, but it's split in terms of the x1 and x2 direction on the disk plus the time direction of the field strength in 3 dimensions. And there is this boundary equations of motion that must be satisfied. So we must choose this Lagrange multiplier A tau in terms of components of A sigma, so that these boundary equations of motion are satisfied. This is not an easy task. So usually people usually takes A tau equals 0, but we need them not to be. We need it not to be trivial. We need it to depend on A sigma. So the canonical Hamiltonian is this one. So the boundary contribution takes exactly the same form as the multiplication of the tau component with the sigma component. And the Poisson bracket is the usual one of a Chern-Simons theory, in which the both fields are conjugate because the action is first order. So the symplectic form of this theory is well known, is the Atiyah-2 form. Is written in the supertrace, and the delta are exterior derivatives on phase space. So using the vector fields induced by gauge transformations, I can find the gauge moment for this theory. It's this one. It takes exactly the same form of a Hamiltonian, but with the test function eta instead of a tau. So the boundary contribution resembles exactly the extended generator of gauge transformation of the monodromy metrics at the poles. So if we perform a symplectic reduction of the reduced space of flat connections, which is well known in mathematics, the reduced symplectic form you compute is just the pullback of the T about 2 form to the constraint surface, to the surface defined by the flat connections. So when you do so, you find that all the information of the theory is contained on the boundary. And the sigma inverse is just a formal notation. So if you invert this transformation, if you compute the inverse, you'll find the calculus of the algebra on the boundary. So this is the fact that a Chern-Simons theory on the disk, after performing the symplectic reduction, becomes the information is completely contained on the boundary, which turns out to be a calculus of the algebra, which is related to a Vesumino with the model. So the gauge I compute the gauge moment again using the symplectic form on the boundary, and then I recover exactly the same form for the gauge generator that you can find using standard Lax pair. So the gauge moment algebra is this one. So it means that on the boundary we have a theory that is described by a calculus of the algebra. So we have the two copies. The K bar means that if you take the first copy, the plus copy, you take K, and if you take the minus copy, so you take minus K, so you invert the level. So the equivalence of the lambda model and the Chern-Simons field on the boundary is this one. It is the extended Lax, not the original one. So with this little dictionary, we can we can show how both theories at these particular points describe the same system. So now I introduce the spectral parameter on the disk. This AI are the two components of the gauge field on the disk, not to be confused with the I tau component. So I do the same, and I can find an interpolating algebra that extends the Chern-Simons algebra. And the S matrix is exactly the same anti-symmetric part of the R matrix that appears in the Maillet algebra of the lambda model. So this is the source of the neutral locality of the lambda model. So now we can try to construct a z-dependent Wilson loop. So let us consider this z-dependent transport matrix in terms of the AI field I wrote before. So using this local algebra, I can compute a well-defined expressions for the two transport matrices at two different points. So you can see how the symmetric part appears in the middle. So this is for two curves that intersect at single point. I mean, I computing something like this. It's very easy. So you have this one. So it's the only contribution of the Poisson bracket. If we have more than one intersection, well, we have to sum over all these contributions. And this is a tricky limit, which I'm proceeding more heuristically here. If the two paths coincide, so we can get this, write this expression this way as a contribution of all the points they intersect. So now I close the loops and I compute the Poisson algebra. So then again, the S matrix, the symmetric part appears in the middle. If I split in this way the tensor product and define some sort of Wilson loop with an impurity, which means that I'm considering this path in this way. I start in this point, And here I insert some, and then continue with the transport matrix until I close it, and introduce that notation. I write the quadratic, the algebra in a quadratic form. So if an interesting case is found when we evaluate the single point intersection bracket at the points. So where the S symmetric part becomes the tensor Casimir. Sorry, we have to drop this Z W dependency. It's just a tensor Casimir. So this last expression is the core of the Goldman bracket. So when punctures and the tensor Casimir are considered in some particular representation, the transport matrices on the right-hand side can be passed over it, and they complete with they passed together with the transport matrices on the left-hand side, and we can resolve the intersection both in terms of some operators on products of loops. So this is some sort of spectral parameter extension of the Goldman bracket. There is something interesting here because we are working in the disk. So people might say, if you're working on the disk and you don't have any obstructions, all Wilson loops will be trivial. But this Z-dependent Wilson loop always depends on the area. And we can show that if we impose the simplicity reduction of the theories on the 2 points simultaneously and compute the curve that depends of Z, which is defined in this way and required for in the formulation of the non-abelian Stokes theorem. So we find this answer. So we cannot cancel. The loops are not independent of the path. They depend of the inverse of the twisting function. So the Wilson loop is only flat on the poles. The X is a combination of commutator that never vanishes. So there are two ways to consider Wilson loops non-trivial on the disk. By introducing punctures, which is the usual strategy, in the sense that the gauge field is flat everywhere except at some points, or by introducing this unspectral parameter in which we can, in which the twisting function plays the role of the obstruction. So the equivalence between the two models at the boundary, now including the spectral parameter, is Z. So if I denote the Wilson loop defined on the Chern-Simons formulation, but with a loop around the circle of the boundary of the... I'm sorry? Okay. No, yes, I know. So it's Chern and Simons. Yeah. Okay. 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 So this is the link between the two theories. So if I denote the WZ, the Z-dependent Wilson loop in Chern-Simons theory, but around the boundary or the circle. So after the simplicity reduction, we should have the correspondence between W and the monodromy matrix of the lambda model. And the important part is the following. After I perform the simplicity reduction and consider under the smooth the algebra structure that lives on the boundary, the monodromy matrix is conserved because it is strongly flat. The Lax pair is strongly flat. So we recover the the conservation of the infinite number of quantities. So the picture is more or less this one. So you have a spectral parameter dependent bracket on the Chern-Simons theory, which under simplicity reduction becomes the Maillard bracket, which is the problematic one because of the neutral locality. That path of the path order exponential is the well-known problem, which means that the Poisson bracket of the monodromy matrix is unknown. But on the other side, we can work in this way and construct a local bracket for these W's. So the conclusions are the following. So the theory living in the boundary, after including the spectral parameter, very carefully, the theory living on the boundary of this Chern-Simons theory is just the lambda model, just mimicking the connection that exists between Chern-Simons and Wechsler-Minowittian connections, Wechsler-Minowittian models, the chiral one. So we can bypass this problem of the non-neutral locality of the lambda model at the cost of introducing two extra first-class constraints. They are first-class if we run the Dirac algorithm, not just the symplectic formulation, in a theory of one dimension higher. So, under an eventual quantization of this, including the spectral parameter, obviously, a potential advantage is to consider a quantum theory on the disk of finite size. So, of finite size closed string, but the quantization will run exactly in an exact way, because Chern-Simons is a very known theory, quantized in many ways. So this is the first part of this little project, and when I hope to be continued later. Thank you.